Today I'm going to talk about a topic which is of extreme importance to the current situation in the United States and across the world, which is given a limited number of vaccinations, what is the most effective way to distribute these vaccines in the population to reduce death or serious illness? And I think there's some analogy, all of you like ideology scholars can trace between maybe vaccinating against these, but I'll let you speculate on that. So this problem has been studied a lot. There have been a lot of analytic as well as simulation-based studies going back at least 2 decades asking who should we vaccinate first. This literature has shown pretty definitively that it does matter in social networks who you vaccinate, and that the most central individuals should be vaccinated first. So this is, in a lot of settings, a reaction against the knee-jerk, we should vaccinate the most vulnerable. It turns out like vaccinating the super spreaders makes more sense in a lot of cases. So this project is mostly a replication and a little bit of an extension of previous results, and also maybe just to refresh all of your memory on something that you haven't quite seen before. So the simulations are based on this really great data, freely available, and I've been wanting to use it for years. So these are almost real-time close contact networks within delimited settings. So like schools, the workplace, and various events. So the participants of the study will wear these small devices on the right around their neck, and these devices communicate with each other, emitting low-energy Bluetooth signal packets at a regular pace, which identify the device that's emitting them, and they're also listening. So the signals don't travel very far, only 6-10 feet, and even less so through a body, and you can tell by the signal strength approximately what the distance is. So whenever one device hears the call of another, so to speak, a tie is recorded. And the result is that the data set I downloaded, fortunately I didn't have to collect this, for each 20-second interval throughout the school day, I have the presence or absence of a close contact tie between each pair of participants. So let me show you what that looks like, hopefully. So here, we're just speeding through Monday right now. This is a high school in France in 2013. Oh, sorry. And it's start my video? Okay, sure. So there's 3 grade levels in French high school, and each of those grade levels are split into 3 classes. So each of these blue circles represents one separate class, and you can see that for a majority of the day, they're interacting. Well, here, that was lunchtime, that blast of energy, and then they're back in their individual classes, and by the end of Tuesday, there's some other rejoining. Beginning of Wednesday, there's sort of a cross-class interaction that happens very briefly, presumably in the hallways, another lunchtime. So you can see this is really dramatically fine-grained data, and actually each of the snapshots, each of these networks are an aggregated 15-minute interval. So it's even more sort of fine-grained than what you see here. And let me, if I can, so here's the aggregated data over the course of the entire week. And what I'll do is, the simulation is very simple, simulating disease spread. I infect one student at random with a highly infectious disease, which, and for each of these 20-second intervals, whenever the infected person or any infected person interacts with somebody who is susceptible, there is some small probability that in those 20 seconds the disease spreads. I also have a recovery sort of state. There's some probability in each time period that they will recover from the disease. So I can show you what that looks like. So here in the lower left, we see the first infection spreading to a couple classmates and, unfortunately, into another class. I picked a particularly bad run where everybody ends up getting infected by the end of the week. But the situation for this disease is not good. So just one infection, if we run this simulation hundreds of times, 14% of the simulations don't get more than the first infection, the one that we caused. So the student we infect doesn't spread the disease at all before recovering. But when there is a second infection, on average, about 77% of the remaining students are infected. So that's pretty dire. The goal now is to save the school. So for simplicity, let's say we have 50 vaccinations and that the vaccine is 100% effective, although these parameters can be modified in the simulation. If we distribute these randomly throughout the school, it's 50% more likely that there is never a second infection than if we don't vaccinate at all. I don't think I mentioned there are 330 students in this school. So 50 is a pretty small proportion. When there is this second infection, so the first person infects another, the average number of infections is 45% of the population, down from 77% without vaccination, which is a significant improvement given we've only vaccinated 15% of the population, but other strategies do much better. So I'll present the results from a few different vaccination strategies in a table. Let's see. Okay, so at the bottom here we have what happens if we do nothing. So 14% of the simulations have no second infection. Okay, so the first person recovers before they're able to infect somebody else. 78% of the simulations have more than 50 infected individuals by the end of the one week. And this third column is the, given that there is more than one infection, what is the average percent of the school, and more precisely, the percent of the as yet unvaccinated students who get infected. So with no, I've already described none and random. So this is randomly chosen vaccinations. Here is a contact strategy. So contact, friend, and friend high degree. These all operate based on the friendship paradox, which says that your friends on average have more friends than you do, because when you select along a friendship, you're selecting those who have more friends. So for instance, friend, this strategy chooses a random, so 50 vaccinations, 50 individuals, and then have each of them choose a random of their contacts, any of their contacts. Contact is similar, except you choose 50 random people and some random time on Monday, and you have them give the vaccination to the next person that they interact with. I have a better strategy than this, which is sort of a contact diary, where they look over the next 30 minutes, whoever they interact with the most, they pass it to, and that actually does better than random. This is basically doing the same as random. But the real break here is when we consider, so this friend high degree, you choose 50 individuals and then have each of them nominate their friend who has the most contacts. So you can imagine in a practical scenario, this would be, who do you think is most susceptible to receiving the virus? You could sort of describe to them what you mean by that, and have them nominate somebody who is more important than themselves. Or, more practically, you could probably, they would also get vaccinated, so they don't have to choose between themselves and their friends. This targeted vaccination strategy is just choosing the 50 students with the highest degree. So if we look in this second column, simulations with greater than 50 infections, we see a dramatic drop from 63% of simulations to only 30% for both of these more targeted strategies. And if there is a second infection, the it protects 85% of the remaining population, even though we only vaccinated 50 people. So these are well-known results, which are I'm just replicating on this real-time network, except I think choosing a friend with high degree, nominating a friend who you think is most susceptible. This is something I haven't seen in the literature and will likely be one of the major contributions when I write this up very soon. I still have some time, which is great. So another thing we can investigate is herd immunity. The idea that as you increase the number of vaccinations, at some point you should be able to protect the entire population. So with a random strategy, this in practice only happens at about 70% in my population. These show averages. Another interesting way to look at this is maximums, although unfortunately I was baking this during your previous the previous presentation, so I didn't get to throw that in as well. The main finding, or the main interesting piece here, is we see this increasing protection, this red line, increasing protection of the rest of the student population by randomly vaccinating, and this eventually approaches zero, and we see a much, much steeper approach with either the targeted or the choose a friend with high degree methods, indicating that if you have a limited number, it makes a lot of sense to target these intelligently. And I'll try to move a little bit faster. Another interesting finding from this data set was we can compare the simulation over the temporal network that I just showed you with a simulation over a static mean weighted network. So we take this aggregate network of weighted edges and simulate a week of the same virus spreading, the same day lengths, but it's scaled such that each pair of students contacts each other the same amount of time as in the temporal model. It's just that they're always contacting all of their friends with some proportion. And I don't know if this is so necessary. I might skip it. Here's a animation of this process. And intuitively, so there is no insularity, right? There used to be times during the day when they were confined to their classes. Now there is no chance that the disease will sort of bottom out before it reaches another class. And these intuitions bear out. Here's a histogram of, I think, 100 simulations. And we see that the left is the temporal network, the right is the static network. Remember, the same amount of contact in both networks. In the static network, there is a dramatically shifted number of infections by the end of the week. And again, this is also a replication I just found out yesterday, which is fine. It's great. But there are a lot of future directions. And really, I built this as a tool for others to use. So I will hopefully publish it sometime in the next month and release this code. And the data is freely available for various extensions. And we can talk a bit about that. So we can put differential risk of serious disease and death across the population and sort of correlate that or not with degree, centrality, these sorts of things, and see if there are different choices that you would make with different distributions of risk categories. And also there are a lot of different data sets. So I only did this in a school, but I would like to save a workplace, save an art gallery. So I'll leave it at that. I would encourage you to either email me or follow me on Twitter if you want updates. I wanted to release the code now, but realized that wasn't such a great idea. So, okay, with that, I will stop and ask questions.
Thank you so much, Alec. I am looking at the Q&A. I don't see a question yet. You mentioned a couple possible next steps for other kinds of venues other than schools. Do you have a prioritization? And what do you think about looking kind of outside of a single venue, but really more like daily flows for particular sectors of the economy, so like different kinds of employees.
I think that's a great idea, and I would love to extend it. So, I mean, the immediate extension, I can just plug in the other real-time data sets and examine the differences. So that would be the first step. But this sort of simulation has been run on large-scale, like there was a large-scale contact network that was collected in the UK via cell phone
Right.
proximity.
Mhm.
There are synthetic networks that are built to sort of simulate these sort of interactions between different workplaces, um, different overlapping contexts, and a lot of simulations talking about how different age categories connect with each other. I think I really want this to sort of generalize and be an open resource for extending these findings broader, but I want to stress a lot of this work has been done. So a lot of my contribution is going to be in producing an open source package and likely some theoretical work, right, at least right now, about this difference between the temporal network, which is more close to reality, and the weighted networks, which already are a pretty sophisticated tool if you're studying disease spread. I think often it's a binary network. Tie either exists or doesn't, or more often it's just homogeneous. People interact like they're particles in a gas. And often, I saw a paper that tried to reduce, claimed that this more nuanced temporal network is reducible to this particle representation, and I'm dubious, to say the least. So I think that's an
Thank,
interesting next step.
thank
Immediate.
you. Thank you, Alec. We have a question from Kara Johnson.
Mm-hmm.
Kara asks, is the intention behind including both high degree friend nominations and the targeted high degree approaches to see how well the first works in comparison to the second, since directly targeting high degree individuals is only possible if the network is known?
That's exactly right. So it's an aim to get a more realistic, more practical solution, uh, which I would like. Another great thing about using simulations is that we can construct intractable policies, things that we wouldn't be able to prove anything about analytically, and we can just run an experiment, a simulation experiment, if you will. So, yes, but that is exactly the reason. It's a more practical strategy. And I've also experimented with completely impractical strategies. So one interesting thing you can do is run a simulation with no vaccination hundreds of times and track for each person what is the distribution of the times that they get infected. Do they get infected early and often, or late and infrequently, or some combination of the two? And you can use this then to target the vaccinations, and indeed this does do better than what I've called the targeted strategy. So there's also another edge of this to find the absolutely optimal set, and yes, then to find some practical approximation to that optimal set.